Okay, hi everyone. Okay, hi everyone. My name is Maximus Kanenji, and this summer I worked on using Python to process image data from the Keck Observatory archive. So my mentors were Christopher Gelino and Bruce Berriman. And this was my first time working with astronomical imaging data, and I'll walk you through that project, what I learned, and what I plan to do next. So the first important thing is, what is a supernova? So a supernova is a powerful explosion that marks the end of a star's life, and these events release enormous amounts of energy and can outshine entire galaxies for a short period of time. And astronomers are especially interested in what the regions look like before the explosion happened. So my project was to look at the areas in the sky before the actual explosions happened. Astronomers they find thousands and thousands of supernova events every year. So I use the data from 2024 because that would give me the most time after to see the sky before the supernovas happen. And we're basically finding photos of supernova progenitors. And then I used the NASA extragalactic database to get our list of supernovae. And that's just NED for short. So that's just a database where they have all the supernova events. Okay. So the next important thing is, what is the Keck Observatory and what is COA? So the Keck Observatory is home to two of the largest optical telescopes in the world. Both are 10 meters wide, as you can see in the photo on the right. They're located in Mauna Kea, Hawaii. The telescopes are equipped with powerful instruments like imagers, spectrometers, and adaptive optic systems. The Keck Observatory Archive, or COA for short, stores all the data collected by this instrument. And my project used Python to download and process imaging data from COA so that it can be used for scientific research. And COA is located near IPAC. So why data processing is important? So raw telescope data is often unusable without cleaning. It's noisy, distorted, or misaligned. The accurate data for calibration is critical for detecting faint or distant objects like supernovae. My work aimed to make this data reliable for scientific analysis and for astronomers to have raw, clean data that they can use for their research. So, data acquisition. To get started, I used the Python library called PyCoA, which lets you access and download data from COA. So first, I queried the archive by specifying the supernova target and instrument. Then I downloaded different types of data: science frames, which are the actual image of the sky; dark frames, which correct for sensor noise; flat fields, which help correct uneven pixel sensitivity; and sky exposure, which helps subtract background light. And the instrument I used was NERC2, which stands for the Near Infrared Camera, and it's the second generation. That's what the 2 stands for. It's an adaptive optics instrument, and it takes high resolution images. So each file comes in, so understanding and organizing FIT files. So FIT files are the type of file that we use to open and see the images. So each file comes in a format called FITs, which is standard in astronomy. Organizing the files correctly is critical for calibration. And time frames show the sky before a supernova. And that's what we're going to use in the next slide. So for the calibration process, we have the first thing you want to do is clean up the raw data. So you have to combine dark frames to create a master dark and subtract each dark frame from the science frames that you have. Then you have to combine the flat lamp on and flat lamp off images to create a master flat, which helps fix pixel inconsistencies. And I use a Python library called CCD procs to apply this correction. And these made the images more reliable for further analysis. And you can see some of the code, but I don't think that one works. So on the two images you can see here, we have a dark frame, and that's the lamp on frame. So in the dark frame, the shutter is closed, and you take a long exposure photo to get out any of the hot pixels in the frame. And with the lamp on photo, you can see that NERC 2, the specific instrument, there's 11 instruments inside of the Keck Observatory. So that's with the telescope. And with NERC 2, it has specific, like, I want to say like hotspots that are always in the images. So you can see these black like blobs. Those are not actually from the sky. Those are from the NERC 2 camera. And then that line is always there. It's a hot pixel line. So for the sky frame creation, sky frames are important because they capture the background light from the sky without any bright objects. And I combine several sky exposures into a single master sky frame. Then I subtracted this from the science images to remove unwanted background gradient. And this step helped ensure that only the light in the final image is from stars or galaxy, not from the atmosphere or light pollution. And to make the sky frame possible, you pretty much in the science files they take like about 9 images, right? And they might take more, and they'll basically put the star or a galaxy, whatever they're taking the photo of, in different areas in the sky, so they can see all around it. And you combine those images, so they fit it around the camera, and that will make a full sky that you can use. So, our mosaic generation, once the science images were calibrated and clean, the goal is to stack them into a single clear mosaic. Stacking helps improve image clarity and enhances faint signal, which is especially helpful for seeing distant supernovae. I plan to use AstroPi and a tool called Reproject for this, which helps align images taken at different times. I never got to the mosaic part, but that was one that my mentor gave me. So that's what it would look like if you have the full mosaic and you clean up the images. And in the next slide, you can see what the raw image looked like before and after you clean up the sky and all the inconsistencies and the noise. So it's a pretty drastic difference in what you can see, and you could probably see more things in the sky that were not visible from the 30 images. So for my challenges and lessons learned, I started the project 2 weeks late because my family came over, so I had to spend time with them. I had to catch up very fast. I came in with zero background in astronomy or imaging processing, and I had to learn a lot: what supernovae are, how telescopes and their instruments work, how to access data from COA using PyCOA, NED, and how to use new tools like SAO Image DS9. So that's those images that you can see. That's how they are taken with SAO Image 9. It was definitely a learning curve, and I gained a lot of knowledge and experience. And you can see my mosaic failed on the right side. So that's what my mosaic looks like right now because I haven't finished it. But yeah, I need to work on my code. Sorry. So for results in future work, although I didn't finish completing work, I didn't finish a complete working pipeline. I did make a lot of progress. I developed a full semi-functional system for downloading, organizing, and calibrating the COA data. The full mosaicing and automation are still in progress, and I plan to keep working and improving this project after the internship is over. And I want to thank Dr. Jolino for mentoring me and Mr. Eichen for being patient with my careful history throughout the summer. Thank you for listening.
You have a new love of astronomy, or
Yeah, honestly, I kind of do. I was asking Dr. Jolino while we were walking here, astronomy questions like, what's like the starting pay and stuff like that. Because I might honestly do it. I might like specialize in it because I want to go into computer science for college. So I think I might do like a specialty in astronomy because Dr. Jolino's office mate actually does that. She's a developer for this astronomy program there. So I'm interested in it.
And I was just gonna say, you've already graduated, so you're going to college
Yes.
this year. So you're a little older. You're older than most of our folks because this is your second year in SRC.
Yes.
So are there any other, so you're looking at supernova, but are there other kinds of astronomical phenomena or astronomical bodies that these same techniques can be used to detect?
Yeah, I think there definitely are. I focused on supernova this year for 2024. I only looked at half the sky. So that was 1,333 supernova that was detected this year. And pretty much the same technique applies, because what they do is they find images from the past of that same photo of the sky. So let's just say a supernova happened today. They would go back to, like, let's just say my photos were from 2017. And coincidentally, some astronomer did research on that area for some particular reason, like let's say there was a galaxy there. So if there was something that they wanted to find that happened today, let's just say, they could go back in the past, and that's what my code is aiming to do, is making the job for astronomers easier, so that type in what they want and boom, it will show up. Any other questions? Yes.
So after the mosaic step, how many more process steps are there in the pipeline to get to the finished image?
That should be it, because the mosaic is, yeah, that's the last part, so that final mosaic, or you can see the other one. This is the one my mentor gave me on the right side. It will look like that, but it will have the wider sky frame around it, so that you can see the entire sky around it, see if there was any other things that they didn't see before the supernova happened. And that's just a galaxy, and the core is very bright. It kind of looks like a star because it's being distorted, but it's saturated. But that's just a very bright galaxy. Any other questions?
Thank you.